When a massive commercial vessel needs repair, engineers pump millions of gallons of seawater out of a concrete basin to expose the raw steel underbelly. Walking beneath a 300-meter ship reveals a deeply unsettling reality. Thousands of tons of steel rest entirely on a simple arrangement of temporary wooden blocks. The absolute focal point of this industrial canyon lies at the extreme aft end of the ship, where the titanic propulsion system remains completely hidden from the surface. The solid bronze propeller is unfathomably massive. A single blade on this modern ultra-large crude carrier weighs as much as an entire commercial passenger airplane. After years at sea, this towering golden sculpture returns heavily coated in calcified marine growth, its smooth outer edges deeply pitted, scarred, and chewed away. This severe metallurgical damage does not come from hitting rocks or sunken debris. The solid metal is destroyed by a completely invisible, microscopic fluid dynamic phenomenon. Cavitation occurs when spinning blades drop water pressure so low that microscopic vapor bubbles form and violently collapse. When one of these tiny bubbles implodes against the blade, the localized temperature inside it briefly reaches temperatures hotter than the surface of the sun. These relentless, microscopic explosions act like thousands of tiny jackhammers. They systematically chip away the solid marine bronze, molecule by molecule, until deep craters form in the heavy steel. To repair this, shipyard workers suspend themselves on ropes, wielding heavy industrial angle grinders. They aggressively cut, polish, and re-profile the heavy bronze until the blade shines flawlessly once again. Achieving exact microscopic hydrodynamic perfection demands hours of agonizing, heavy industrial brute force. This polished propeller is useless unless rigidly connected to the main engine hidden inside the hull. That connection relies on the tail shaft, a solid cylinder of forged steel weighing over 60 tons. Extracting this massive component requires a highly orchestrated display of raw mechanical power. Engineers use massive hydraulic jacks and heavy chain blocks to slowly pull the 30-meter shaft entirely out of the ship. The weight of this solid steel cylinder is so immense that if it is not perfectly supported during the extraction process, it will visibly sag and bend under its own mass. Once resting on the dry dock floor, engineers apply sensitive microscopic dye tests, searching aggressively for invisible hairline fatigue cracks in the steel. An unnoticed crack means the ship could lose its propeller and become completely paralyzed at sea. As the tail shaft passes through the outer steel hull to connect to the propeller, it creates a terrifying vulnerability, a massive gap directly into the surrounding ocean. As this diagram illustrates, naval architects rely on a stern tube seal assembly to prevent catastrophic flooding. This complex series of heavy-duty rubber rings tightly grips the spinning steel shaft, blocking freezing, pressurized seawater from rushing in while trapping the internal lubricating oil inside. During an overhaul, engineers use surgical micrometers to measure the clearance between the new rubber and the heavy steel. If this seal wears down by a fraction of a millimeter, the ship faces immediate disaster. A severely worn seal leaking just a few gallons of oil into a harbor causes multi-million-dollar environmental fines and instant vessel detention. The survival of a 300-meter, 100,000-ton steel leviathan against the crushing pressure of the ocean relies entirely on the flawless integrity of a simple ring of black rubber. Directly behind the massive spinning bronze propeller sits a towering wall of red steel. This is the rudder, a hollow hydrodynamic wing that dictates the directional fate of the vessel. The sheer physical scale of this massive hollow red blade is absolutely staggering. Simply pivoting this massive structure a few degrees against the resistance of the ocean requires the steering gear to generate a pushing force equivalent to over 1,000 passenger cars. The rudder is anchored to the hull by massive, highly greased steel hinges, the pintle and gudgeon. As the ship pivots, all that staggering mechanical friction and weight is violently concentrated directly into these internal bearings. Steering a massive commercial vessel is an exercise in focusing the brutal force of the ocean into localized, concentrated friction at a single, highly engineered pivot point. With the structural and mechanical components restored, the shipyard must intercept a final, silent enemy that begins attacking the moment the hull touches saltwater: galvanic corrosion. This schematic traces the electrochemical reaction. Because the massive bronze propeller is highly noble, it inadvertently acts as a giant battery terminal, actively pulling electrons out of the weaker carbon steel hull and aggressively accelerating rust. To defeat this invisible electrical current, shipyard workers weld dozens of chunky, rectangular blocks of dull gray zinc directly onto the pristine red paint. These are sacrificial anodes, engineered to be chemically weaker than both the propeller and the steel. They intentionally dissolve into the ocean, absorbing the electrical damage and shielding the multi-million-dollar hull. Massive valves open, flooding the basin with freezing seawater, silently lifting the newly restored mechanical tail off its wooden blocks. Keeping a cargo ship alive demands a constant balance of roaring power and microscopic atomic-level precision. But this massive external propulsion system cannot move without the powerhouse inside. Next time, we cross the watertight bulkhead to explore the grease-choked, blistering reality of a main engine machinery overhaul.